Okay, so this lesson is over direct variation, which is really just another word for proportional relationship. So you're going to hear a lot of the same things that you've already heard because this is just, like I said, a different vocabulary word, but same thing as proportional. So it says two data sets have direct variation if they are related by a constant of variation, called the constant of proportionality. We've already used that term before in class, so this should sound familiar. And it says the graph of the data sets is linear and passes through the origin. So we've already talked quite a bit about proportional relationships have to go through the origin. We've also mentioned this form of the equation, y equals kx, and we talked about using y over x to determine if it is proportional. So they're using the words constant of variation here. We've also used the words constant of proportionality, direct variation, proportional relationship, all the same stuff. Okay? So let's move on down to this portion of the worksheet. It says determine whether the data set shows direct variation, or in other words, is it proportional? If there's a constant of variation or a constant of proportionality, identify it and write the equation of direct variation and plot the points and tell whether the graph is linear. Okay, so if it is a direct variation or a proportional relationship, we should be able to do y over x and it remain constant. So 8 divided by 1, y over x, we do 8 divided by 1, that equals 8. Here if I do 4 divided by 2, that equals 2. And this one, 2 divided by 4, that equals 1/2. And this one, 1 divided by 8, well, that equals 1/8. There isn't a constant of variation. They're all different. If I do y over x, I get different values for each one. So is there a constant of variation? No. So I don't need to write the equation. There's no constant of variation. Is the graph linear? Well, let's see. Let's graph the points. This is x comma y. So the points that I'm going to graph, I'm going to graph 1 comma 8, 2 comma 4, 4 comma 2, and 8 comma 1. X comma y. Okay, let me write that. Alright, so 1/8 would be over 1 and up to the 8. 2/4 would be over 2 and down to the 4. 4/2 would be over 4 and up to the 2. And 8/1 would be over 8 and up to the 1. So this clearly does not form a straight line. It's not linear, so no. Alright. Constant of variation. You know, already I'm seeing that this goes through 0, 0. So I already know that it's linear because it's, well, maybe not. Let me not jump ahead. Alright, let's do y over x. So this would be 20 over 2, which equals 10. This would be 30 over 3, which equals 10. And this would be 50 over 5, which indeed does equal 10. So is there a constant of variation? Yes, it's 10, right? So if yes, what's the equation? Well, remember, the equation looks like this. It looks like this, y equals kx. So the equation would be y equals, there's my constant of direct variation, 10x. I know it's going to be linear because we've got a proportion here, but I'm going to go ahead and graph the points. It goes through 0, 0. That's why I was already leaning towards saying this was a direct variation, because it goes through the point of origin. Then I'm going to go for this next one, over 2 and up 20. Remember, I'm using these as my points. I'm using 0, 0, 2, comma 20, 3, comma 30, and 5, comma 50. So over 3 and up to the 30 would be right there. Over 5, excuse me, and up to the 50 would be right there. So are they linear? Do they fall in a straight line? They should, and they do. So is it linear? Yes, because it forms this straight line when I graph it. All right. Next page says, when quantities are related proportionally by a constant of variation, they have direct variation. This is all just the same stuff, just restating that it's proportional. This table shows the relationship between the number of glasses filled and the amount of juice needed to fill them. The amount of juice needed varies directly with the number of glasses filled. So if you'll look, y over x is always equal to the same thing. 8 divided by 1 is 8. 16 divided by 2 is 8. 24 divided by 3 is 8. 32 divided by 4 is 8. So it says, what are the quantities that form this direct variation? What are the quantities that form this direct variation? To be honest, I don't even know what that question is asking. Hang on. Won't let me pause it. Of course not. Can't just pause. What are the quantities? Let me skip that and maybe it'll come to me in a second. But what is the constant of variation? Remember, constant of variation, same thing as proportional, same thing as constant proportionality. When you hear this language, you need to start thinking y divided by x. So, this is x and this is y. Alright? So, I'm going to put y over x. That equals 8. Already went over this. 16 over 2. That also equals 8. 24 over 3. That equals 8. 32 divided by 4. That equals 8. So my constant of variation is this 8. Okay? My constant of variation is 8. Alright? A graph of a direct variation is always linear and always passes through 0, 0 because it's the same thing as a proportion. So number 3 says, what do the x values on the graph stand for? Well, we said up here in the table that the number of glasses was the x-axis, and the y-axis would be the ounces of juice. Alright, so what do the x values on the graph stand for? Number of glasses. What do the y values stand for? The ounces of juice needed to fill them. Alright, what does the ordered pair 2, 16 mean? Well, it means 2 is the x, this is the x, and this is the y. So, we've got 2 glasses, right? Because this is on the x-axis and the x-axis is glasses. 2 glasses is filled with 8 ounces of juice. 16 ounces of juice. 2 glasses, 16 ounces of juice. I'm not going to try to correct that. That's a 16. Alright. It says write an ordered pair for 3 glasses and the amount of juice needed. Well, the glasses is my x value, so I know it's 3 comma, right? And 3 is paired with 24 ounces. And the amount of juice needed. You just go over to the 3 and up to the 24. So this would be my ordered pair. That's it.